Welcome to Digitalized in Stockholm 2023 and the presentation of the project Democritus, Decision-Making in Critical Societal Infrastructures. I am Bengt Dahlgren from RISE and Johan Karlsson from KTH will join me for part of this presentation. In this project, we work with digitalization to develop smart monitoring and control based on data-driven methods for critical infrastructures with the purpose to increase resilience, safety, and efficiency. This involves monitoring for scheduling normal maintenance as well as finding and handling faults. There are many examples of such large-scale infrastructures that the modern society depends on. We have roads, buildings, train tracks, bridges, and other built infrastructure. We have a digital infrastructure with communication networks and computation. We have infrastructure for utilities such as water, heating, and electricity. And we also have emerging large-scale distributed applications. The project team consists of members from KTH, Stockholm University, and RISE, with Victoria Fodor as the project leader. What are the scientific challenges we have to address for large-scale monitoring and control? Well, monitoring data are distributed over potentially very large distances, which either then have to be collected to a central location or computed on locally. Local distributed computation can be desired for reasons of privacy, scalability, and/or performance. So distributed learning methods capable of handling large-scale distributed data sets are desired. New network designs that support learning applications provide new opportunities, combining communication with computation in the wireless domain. The third area is new methods for modeling and analyzing physical systems driven by monitoring data. In the project, we here focus on water distribution networks, as we will see a bit later in the presentation. Finally, we need methods to evaluate our solutions, since it normally isn't possible to experiment with the real large-scale critical infrastructures. Well, for reasons of not possible to access them, but also that they are critical and we cannot interrupt the regular operation. But what we need then is methods for evaluation that involves aspects of communication, learning, and the actual operation of the physical infrastructure.
Hello, my name is Johan Karlsson, and I will give you a brief overview of some results in this project relating to challenges in water distribution networks. So there are several reasons why there is a need to develop new methods and models for water distribution networks. So currently, the current infrastructure has a relatively low degree of or low level of digitalization, at least compared to other infrastructures such as the smart grid. But with the current digitalization trend, there will be more and more sensors to be available, and also need for new methods that can analyze, diagnose, and control these networks. We may take access to cheap and clean water for granted, but in many parts of the world, water is a scarce resource, and water leakage can have huge damaging impacts on the society. Also, contamination is a big problem. Even though these events are not so common, they can be very damaging when they occur, need to be identified as soon as possible. So one part of the Democritus project is to develop methods for leak detection. So currently there is a large amount of data collected by the smart water meters. And in this project, we will take this data in order to quantify and localize leak. And in particular, the methodology uses pressure and flow data to determine and localize the exact location of the leak, including the pipe and the pipe location. And some of this work was presented at the ECC 2022. So for the cases when the model for the water pipe is not known, this can be determined using database models. So in this here, we can see that a scenario where the water flow and the pressure are measured continuously. But we can also see that as more and more data measurements becomes available, the corresponding model will be better and the estimates will be improved. A particularly challenged scenario is when there are parallel pipes between the measurements. In this case, there are typically several possible leak locations that can explain the pressure and flow measurements. But one way to get around this problem is to jointly process the data collected during different working conditions. So in particular, one can analyze the flow through the pipe or through the system at different pressure levels. So the figure on the right shows one such scenario, and here we can see that if one tries to explain the measurements with a leak in pipe 2 or pipe 1 or pipe 3, the corresponding location of the leak would move. However, if one explains the location with a pipe 2, then it stays constant during the different pressure levels. So therefore, in this case, the pipe 2 is the only plausible explanation for the leak. In this project, we also consider pollution tracking in using ensemble Markov models. So in this case, we consider this as a hierarchical problem, where one level is the water distribution network, or the water flow, and the other part is the pollution flow, or the pollution levels within this water. So first, we use data from EPANET that are based on water usage and water flow measurements to build a time-varying ensemble Markov model for the water flow in the system. And then we use the pollution measurements in this model in order to track the evolution of the pollution. For several parts of this project, we use EPANET, which is a widely used simulation tool for water distribution networks. One of the use for this is, of course, for creating training and test data that we can use to develop and determine the parameters of our models. However, note that EPANET is a model for computing flow and pressure given the current state. There's many more complex scenarios that EPANET cannot handle directly. So, for example, if you want to adapt flow and pressure based on some partial measurements of the system, or if you have some noisy measurements with some certain noise distributions. In this project, we have therefore integrated EPANET with Python so that we can utilize the EPANET simulations within our method and thereby addressing a wider range of problems. This would also allow for integrating our method for water distribution networks with methods for learning and network design for distributed data.
And now the last part of this presentation, where I will talk about learning and network design for large-scale distributed data. So network for learning. As mentioned earlier, there might be large amounts of monitoring data. So instead of collecting them centrally, it is desired to use distributed computing locally closer to the data. For example, making use of on-premises computing or edge computing provided by a network operator. Sometimes fully accurate data is not needed, but instead a function of them, like the sum or average of the independent inputs, is sufficient. And this is something that we would like to take advantage of in our work. So not needing accurate data is normally the case when training a machine learning algorithm. Learning is carried out with a function of the input data, for example, the sum of the gradients. You can therefore say that orthogonal, that is the independent transmission of exact individual data values, is a waste of resources in wireless networks. So we propose analog and digital techniques for reliable channel computing over noisy networks. So the scenario is that we need to perform training of a machine learning algorithm over hierarchical, mixed, wired, and wireless networks. So our hierarchical learning and transmission scheme applies over-the-air computation in the wireless network parts, so it there becomes scalable in terms of bandwidth usage. And it successfully mitigates the effect of intercell interference with the help of learning parameter optimization. In the figure to the right, we can see that accuracy of our proposed method using over-the-air computation in purple comes fairly close to the method with orthogonal transmission of exact values in green. So digital communication and computing systems as critical infrastructure have to deal with cyber attacks. Detection and mitigation of these attacks needs to become automated. So in this work, we study automated intrusion detection in an IT infrastructure, specifically the problem of identifying the start of an attack, the type of an attack, and the sequence of actions an attacker takes. The method is based on continuous measurement from the infrastructure. We apply statistical learning methods, including hidden marker model and long short-term memory to map sequences of observations to sequences of predicted attack actions. So finally, we present a slide here with selected publications from the project for reference. And thank you for listening.